And as James said, so I did my master program in UCL and majoring in geospatial sciences. And now I'm engaged in work related to intelligent transportation. And what I'm going to talk about today is a research on visual walkability assessment in London, reflecting pedestrians' walking experiences. The outcomes may contribute to walkability optimization in London and improve upon the urban planning. So we begin with walking and walkability. And walking can be easily incorporated into residents' daily life. And in addition to being an environmentally friendly mode of transport, walking contributes to physical and psychological well-being. Thus, increasing the walkability of city streets to encourage walking is a key policy goal for many cities. Historically, London has always been a walking city, and walking is currently at the forefront of the mayor's plans for transport in London, illustrating an ambitious vision for transforming London into the most walkable city in the world. And walkability illustrates the extent to which the built environment supports and encourages walking throughout the road network. It has been thought as a foundation for city sustainability, and constituent components to describe walkability can include various factors related to the built environment corresponding to different research scenarios. And these include street connectivity, destination accessibility, pedestrian infrastructure, traffic and coordinates, mixed land use, and so on. So, move to the next page. However, being a part of the urban transportation network, roads also act as public leaders areas. As the development of modern road networks and urban architecture proceeds rapidly, central London streets become clogged with cars and other modern facilities. The quality of London as a walking environment declined, and the needs of people walking began to neglect it. It started to cause great damages to Londoners' walking experience. Therefore, psychological and subjective comfort of pedestrians are referred as key factors for walkability. And we can look into the previous studies. And previous studies into walkability in London are mainly associated with physical environmental attributes. A walkability index for London at neighborhood level has been constructed, and you can see on the right top is the results of the research. So it has been constructed from multiple factors, including residential dwelling density, street connectivity, and land use mix. And then in the walking action plan, walkability was investigated at street level in the context of pedestrians' walking frequency, and found that people living in areas with dense, mixed-use, integrated buildings and with good access to public transport are more likely to walk. But walkability assessments in terms of pedestrian psychology are still missing. And besides, researchers are often make their research by audit methods and participatory research techniques. For instance, field trips, field surveys, and questionnaires. But these approaches are deficient in time and physical cost. So in our study, we employ the integrated visual walkability framework using street view imagery combined with computer vision method to assess the integrated visual walkability across inner London streets. And the framework was first built by Joe, etc. in 2019, and was applied to the IWW assessment in Shenzhen, a city in China. So in their research, the results represented a great heterogeneity across the streets, showing the usability of the framework. But in our research, it's an attempt to apply the framework to a large data set. Then in the following part, we will talk about our research methods. And first is the study area and data. And as we know, inner London and outer London has been defined in the spatial development strategy raised in the London plan since 2004. And inner London covers an area smaller than outer London, but in terms of population, it has more than double the population density of outer London. And therefore, in this research, we concentrate on the inner London area. The raw network data is obtained from the Organised survey, and there are over 63,000 in this data set in total. The Street View images are assessed using the Google Street View static API, and in the URL, the location parameters of Street View imagery are determined by the geographical location of roads in the network, and the heading parameters, we set it to be 0, 120, and 240. The page is set to be 0, and thus three images can entirely cover the physical environment at one site. The SegNet network is applied in this study to realize image segmentation, which is a deep convolutional encoder-decoder architecture for semantic pixel-wise labeling, and which comprises a set of long linear processing layers and their corresponding group of decoders with a pixel-wise classifier following. And when RGB image is input into the architecture, it will be processed first by the encoder network. As shown in the figure, you can see the blue layers, which performs convolution with a filter bank to produce a set of feature maps, and then bunch normalized. Afterwards, an element-wise rectified linear long linearity is applied. And subsequently, the max pooling process will be carried out. It is a downsampling of an image aimed at reducing the resolution of the feature map while retaining the important features. And to store boundary information in the encoder feature maps with a memory saving approach, the max pooling indices are involved. And by using the max pooling indices, the decoder network can upsample the feature map passed from the encoder network and produce sparse feature maps. Then these maps will be convolved with a trainable decoder filter bank to conduct dense feature maps, and then normalize, and we got the output image. And the CAM-with dataset is used to develop a useful SegNet, which contains 367 training and 233 testing images of road scenes taken around Cambridge, and with both day and dusk scenes inside. Then the trained SegNet model is used to realize segmentation of the street view imagery, and our pixels of the input images are labeled with a corresponding category. To apply initial outcomes for walkability calculation, pixels are reclassified, as shown in the figure. So the categories of tree, sky, pavement, road, building, and fence are kept, while the rest of the classes are merged into a single new category called obstacles. And additionally, To remove the salt and pepper noise in the output images, the mating filter is applied. Then well-labeled images are ready to be used in the assessment of visual walkability. So the integrated visual walkability framework introduced in this study was proposed by Joe, etc., being used as a matter of psychological and subjective comfort for pedestrians by simulating the impact of street features to pedestrian subject perception and extracting indicators from pedestrian experience. 4 sub-indicators are constructed and united to form the integrated visual walkability index. And 4 dimensions include greenery, crowdedness, outdoor enclosure, and visual pavement. And the sub-indicators are calculated by the number of pixels from different categories as shown in the table. So there's 3 viewports at each location. So we use them together to get the calculated results for one location. Considering the impact of central visual field and the accuracy of segmentation, we don't directly use the calculation results, but to classify the values into 5 levels. And level 1 represents the least walkable, while level 5 represents the most walkable. The table describes the classification standards applied in this research and includes samples from different levels. So after our process, we can get the IWW of each road in inner London, and we can look into the spatial patterns. The spatial patterns of IWW at street level are shown in the figure on the left, and the distribution of IWW shows great variation across the study area. Field clusters can be found in the results at this scale, neither high or low, which means roads at different visual walkability levels have a mixed distribution. And to comprehensively analyze the form of the distribution and to provide improvement measures for city designers, distribution of 4 sub-indicators are also shown on the right. And we can look into some details. Sorry. So it can be found that the average greenery across inner London road network is at a low level, and that high level appears around the green lines like Hyde Park and Regent's Park, and no obvious regularity can be found at other street domains, but we can look into some local features. For example, higher density of low IWW streets appears in Marylebone, Mayfair, and Soho, which are busy areas of London, and having the most busy network and most highest network density, and have many pedestrians and vehicles there. So looking to the subdomains, then we can find that low IWW in these areas are result from lack of greenery, too many vehicles and pedestrians, unbalanced design of buildings and roads collectively. And due to the fact that imagery can best reflect the virtual environments of the location, and usually spatial patterns appear based on the characteristics of the built environment, the results need to be analyzed with the imagery combined. Imagery are extracted to test the concordance between IWW and the results of subjective feeling, as shown in the figure on the right side. So streets with high IWW level indicate a more comfortable feeling with more vegetation, large crowdedness, and an appropriate proportion of visual enclosure and pavement. The lower the IWW is, and the worse subjective feeling that will be produced when looking at the images, which can reveal the usability of the framework. And the same conclusion can be drawn from the four subdomains, just like the images on the left side. And still, there are some limitations in this research. And firstly, the Meihui dataset only provides images with similar weather, climate, traffic condition, and urban landscape, making it difficult to interpret complex cityscapes. And secondly, the transplant of IWW framework lacks consideration of London's specific characteristics. The framework performs well in Shenzhen, which is a young and modern city with numerous newly built buildings, skyscrapers, and broad streets were aligned with trees. However, London is an Asian city, which may be unsuitable for planting new trees. And however, this does not mean they will not be perceived as walkable due to their historical and cultural importance. Thus, it can be considered that the sub-indicators are incomplete because they don't capture these more nuanced factors that vary by location. Furthermore, urban vibrancy and safety should also be considered according to the definition of walkability. Other factors such as dwelling density, connectivity, land use accessibility, and diversity of land uses are equally important. Maybe in this way, a more generalizable and comprehensive framework can be established. And here are the references. And yeah, still big thank you to James and Meihui. Also, thank you for your attention.
I'll go through, so Jeremy Morley's got a couple of questions, so let's go with his first. So first of all, what are the terms of use of the API and what are we allowed to do with the results of this research? Good question.
So we can get the location, we can get the coordinates of the roads, and we use one point to represent one link. So use the coordinates of the points, we can enter the location and the maybe page and headings, some other parameters. So we can get the directly get the image of each viewport. So what is allowed using the results of this research? I'm not clear about that.
So maybe I can add to that point because I've been looking at that with Meihui. So you can't cache the images. So you can't just download all the images for a city and keep them. You can have a certain number of requests over a given time period. So we process images to get the semantically segmented image, and then you don't keep the image after that. In terms of potential commercial uses, we haven't really explored that in detail yet. We're more focused on the research aspect at this point. But yeah, with Meihui and Jiaming, we're looking through those to see what we could potentially do about it in the future. But send me or any of us an email afterwards if you want to discuss that more. The second question from Jeremy is, how confident are you with the crowdedness measure? And can you control for time of day or day of the week when various images were captured?
So the crowdedness is not for the crowdedness for people, but is how many obstacles you got in the physical environment.
So I guess if there's, if there's cars parked at certain times, they might not be parked at other times. So maybe that's part of the question. How would you account for that?
Yeah, but maybe the imagery will refresh in some time, but when I get the data, it's just a static imagery. So, but we try to decline the impact of the time when we get the imagery, and we use the level, but not the directly calculated results. So.
Okay, so we have another question from Nick Ham. How do you validate walkability?
We firstly use the imagery along with the IWW, but due to the limitation of the time, so coronavirus, so we can't get to the streets to maybe give some questionnaires to some pedestrians. So maybe the work can be done in future.
Yeah, I think that's something that Meihui is going to be taking on because we noticed that definitely between Shenzhen and London, the cities are so different that you can't really use the same measure to estimate the visual walkability. So that's something we're exploring. And then another question from Phil Barty. Have you carried out any comparison of your results with map data? For example, master map data has pavement polygons. Thinking particularly on streets with crowded parking where views of the paved area may be occluded. And also, did you note lower values near corners where the view ahead and behind might be more limited?
I don't think it's comparable. Actually, we use one point to represent a link, and when we get the imagery, the API will get the closest available imagery to your coordinates. So it's not an accuracy point, but it can represent the condition nearby. So I don't think it's comparable.
Thanks for that. So that's the last of the questions in the chat. Hopefully, those of you who asked a question, Jiaming has been able to answer those as well as you would like. If not, feel free to email us. I think you can see in my camera screen there, it's got my email as my name. That's not intentional, but you can use that to contact me. Jiaming's very busy working for Tencent now in China, so she might not be able to get back to you as quickly. So thank you again, Jiaming. Very interesting talk, and I think everybody will agree that's a lot of work to do in 3 months. So well done for that.